All right, for this final section on photoelectric effect, we're going to do a few things, but the first thing we're going to do is calculate the work function of a material that is on that surface. So in this setup, when I shine a frequency of light that is beyond the threshold frequency, we're going to eject electrons, and then when I apply certain voltages or stopping voltages, I can calculate the kinetic energy of those electrons. And this setup was instrumental to be able to categorize different materials in terms of their ability to release electrons. And categorize them based on their work functions. So if we take a look at this classic problem where it says that a photoelectric surface in a cell is illuminated with 250 nanometer light, that's like UV, ultra UV light, a stopping voltage of 0.911 volts must be used to reduce the current to zero. What is the work function of the surface used in this cell? So in order to answer that, we first have to plug in a formula. Oops. Okay, so the formulas that we had was the kinetic energy of the electron that is emitted is equal to h times the frequency of light being used minus the work function. So in this case, if we're trying to calculate that work function, I can rearrange the equation. So kinetic energy minus hf is equal to the negative work function. Okay, and what would that kinetic energy of that electron be? That would be the voltage, the stopping voltage, multiplied by the charge of an electron, minus Planck's constant times the speed of light over the wavelength, and that's going to equal to the negative work function. Okay, so I'm just going to move this over, so if I plug these numbers in, 0.911 volts multiplied by 1.6 times 10 to the minus 19 is the coulombs, which is the charge of an electron, okay, minus Planck's constant times the speed of light divided by the wavelength, which is 215 times 10 to the 9 meters, okay. If I put that all through in a calculator, I should get 7.79 times 10 to the minus 19 joules. Now, it's not often that they calculate work functions in that because it's a very big number. What they do is they convert that into electron volts. So that number divided by the charge of an electron would give me the electron volts, which is what we usually use for the work function. So if you go through that and calculate that again to find that answer, that would be the process of calculating a work function. And a lot of questions based on this, they would either give you the work function, you got to calculate the threshold, calculate the threshold frequency if I had the work function, okay, or they can ask you to calculate the stopping voltage or the frequency of light being used. So remember, if I wanted to calculate the threshold frequency and they gave me the work function, well, the threshold frequency is HFO. So if they gave me the work function, or I just calculated the work function divided by Planck's constant would give me the threshold frequency. So you'll see in the practice problems in your text and practice problems that I'll be giving you in class that there's many variations from the information they give you in this problem that you can calculate a variety of things using the photoelectric effect. Now, the next section is that you're required to do is if you were going to do an experiment with this setup, which we're going to do as a simulation, one thing I can do is I can vary the wavelength that I'm using shining on here, and I can see how does a change in the wavelength, or better yet, the frequency that I shine on here on a metal surface affect the stopping voltage needed to stop the electrons from flying. So if we did that experiment, you're going to get a linear graph if you plot frequency versus stopping voltage. And that linear graph is going to eventually have an intercept. Okay, so what's required of us is to know what is the meaning of that intercept and what is the meaning of the slope of this graph. So if we write this out again, so kinetic energy is equal to HF minus the work function. Okay, so and kinetic energy is the voltage times the charge of an electron. Okay, so if I linearize this equation according to this graph, I just have to move that charge of an electron over to the other side, and I'll be getting the voltage is equal to HF minus phi over an electron. Okay, and that would explain to you why the slope of this graph, the slope of that graph would represent the Planck's constant divided by the charge of an electron. And this over here, if I take the work function divided by the charge of an electron, that would represent my threshold frequency. So that is FO. Okay, that's our threshold frequency. So whenever you see the intercept on this graph, that means the threshold frequency, and the slope of that graph is Planck's constant divided by the charge of an electron. So you might have to process that data on an exam if necessary. Last thing, we talked a lot about how if I change the intensity of light that is impacting here, not the wavelength, but if I change the intensity of the light, what happens? Well, if I change the intensity, this graph is showing us what will happen. Low intensity, the graph looks like this. High intensity, the graph starts from the same place, but just grows. And that's because intensity is watts per meter squared. It has more energy per meter squared. And energy relates to the number of photons that are incident on a surface per second. So if I increase the number of photons per second, I'm going to increase the number of electrons emitted, and that's why I get a steeper slope. So we start at the same stopping voltage. That's because that stopping voltage relates to the threshold frequency and the work function of a material. If I change the material, what would happen is I would be changing where that graph starts. So if I change from potassium to sodium, I'll be changing where that graph starts. Okay, that's about it. You can follow up a little bit more in your text to get a little bit more information, but that's as much as you're probably going to need for your notes.